Okay. Okay, then good morning, everyone. Welcome to the lecture number 9 of this course on quantum simulations. I have switched the topic with respect to the syllabus. And today I would like to tell you about the ideas of thermalization, and quantum scars. Okay, so I would like, first of all, to begin by discussing thermalization in classical systems. So we should start by speaking about classical systems. I know some of you may be taking a course on classical chaos by Yitzhak Dana, so you're probably more expert than me by now. But for everyone, I'm going to give a brief introduction to the concept of chaos. So actually, let me start by a simple example. So let me start about, classical, a very brief introduction on the topic of classical chaos. So let me start with a simple example, which is just an harmonic oscillator. And in particular, I would like to discuss the harmonic oscillator in the phase space. So this is X and this is P. Okay, this is phase space. So as you all know, an harmonic oscillator in phase space is it's like a rotating particle, right, in X and P. So you start at a large distance, then you accelerate towards the center, so P grows, and then you reach the back, the left-hand side, so minus X, and then so on and so forth. So it's like a circle in X and P. And one may ask, what happens if you if you consider a more general system, like say a nonlinear system. So of course, in the case of nonlinear system, so this is my harmonic oscillator. So let's now consider nonlinear system. And here, of course, the dynamics is going to be different. So, if the system is really nonlinear, this will be completely changed. You will obtain some other path in X and P. It's going to be very different. However, the point is that still the system will follow some well-defined trajectories, and the trajectories will not cross. And we do not expect to have chaos. So meaning that if you start from, so you all know the definition of chaos, it means that if you start from two positions that are close by, you ask yourself, do I end up in places that are very far apart? And this example is a system in which this does not occur, meaning that if I started with a slightly different initial condition, so instead of here, let's say here, I would probably, follow a slightly different path, but eventually I will come back to I will still be close to the initial conditions. I mean, the system, the two trajectories will not go apart one from each other. And the reason for this is that we have integrability. Okay, this is a system that is integrable. And here integrable means that there are many conserved quantities. Well, in this case, there is one conserved quantity, which is the energy. Okay, I'm considering a time-independent nonlinear oscillator. So there is one conserved quantity. And as a consequence of this conserved quantity, I need, if I start, so the initial condition will define the value of this conserved quantity. And I need always to follow the path associated with that conserved quantity. And as a consequence, for instance, I cannot cross, two patterns, two trajectories cannot cross, because if they crossed, it would mean that they actually have the same value for the integral of motion. But this is impossible. Okay. Hi everyone. So I see that some of the class is in a frontal meeting. Which is great. Okay, good. So can you all see me in the class?
Yes, we can see, we can hear.
Okay, excellent. Okay, very good. So So this is what I want to say. And so an example of so these two systems are systems that are integrable. Okay, so basically, why they are integrable? Because there are just two coordinates. You have just two coordinates and one conserved quantity. So then, as we discussed, the phase space picture must be very simple. You cannot have crossing points, and you just need to follow some path, which may be some nonlinear, some complicated path, but there are just some path that cannot cross. So what would be the simplest example of a chaotic system? So a chaotic system is basically a system that is non-integrable. It would be, for instance, a kicked rotor. So a kick rotor is just it's like an oscillator. It's a nonlinear oscillator in which the energy is not conserved, meaning that because you kick it, so you have a time-dependent Hamiltonian, and therefore the energy is not conserved. And this is basically the simplest example of a system that can lead to chaos. Because you have two coordinates, but there is no conserved quantity. Okay, so this would be an example of two coordinates and no conserved quantity. So what will happen? Essentially, what will happen is that as you start, this is a system in which if you kick the system very, very, very rapidly, then it is essentially the same as having like a constant force, and therefore there is no chaos. But when you decrease the velocity, the frequency of these kicks, then you start seeing some areas, some small regions of chaos. So you start seeing some small regions, some chaotic regions, and then these chaotic regions become larger and larger. And let me share with you some picture. I think this is a nice example of a problem that gives rise to nice pictures. So let me show them for you. Let me open it up here. Okay, this is from Wikipedia. So I just share with you my screen. Okay, so this is basically these plots that you see. How many of you have already seen those pictures? Raise your hands. No? More, okay. So more is following the course on chaos. Okay, good. So I think this is maybe it's not related to quantum physics, but I think this is a mass. So this is you understand what it is. This is just a nonlinear oscillator that is kicked as a function of time. And what you see is here, each picture. This is a phase space. So this is X and P. In this system, the nonlinear potential is periodic. It's a cosine potential. Therefore, you really need to think of this as having periodic boundary conditions. So you really need to think of it as like a cylinder, basically. Indeed, what you see is that if the kick is very, very fast, then as I mentioned, this is essentially the same as having like a time-independent potential. So the energy is conserved, and you see there are those, there are these patterns, these trajectories that are similar to the one that I've shown you on board. So there are some circles. So some trajectories are closed. Others are closed in the periodic. All the trajectories are closed. Some are closed, say, within one, say, p xp sort of square, and some others are closed using the periodic boundary conditions. So the different colors that just refer to different initial conditions. For any color, you have a different initial condition. So for instance, if you start here for, say, this value of x and p, you will follow this pattern and you will find yourself back to the origin. Or if you started here, then you will go around. This is actually just the minimum. This is the sort of ground state of this is like a little bit like an harmonic oscillator. You see all the circles are like harmonic oscillators. This is a bit more complicated. It's related to the fact that there are periodic boundary conditions. Now, what happens when you decrease the driving frequency? So when you really take into account the fact that the energy is not conserved, there are no more conserved quantities, you see that now the trajectories become more complicated. You see that all the trajectories basically mix up. And it starts for some regions. Here you see there is some region here which is chaotic. You recognize the chaotic regions because you see that all colors mix up, right? So you cannot, the energy is not conserved, so you can move from one trajectory to the other if you want, in a sense. And they sort of mix up and they create some chaotic region. And then the chaotic region becomes bigger and bigger. And until at some point, you will see, just complete chaos. This is really for a very, very weak. Actually, in this system, you can also think of this parameter as the strength of the kick. So this could be, the first picture is like for a weak kick, and then this is for a very strong kick. So this is almost regular. It's not really integrable, but it behaves very similar to integrable systems. And this is a system that is very chaotic. Okay, so it's the simplest example of a system that shows the transition between integrability and chaos. Okay, questions?
So what different colors mean?
Yes, the different colors are different initial conditions. So they are like just different trajectories. The reason that they use different colors is just to make it beautiful. I mean, there is no physical meaning to the colors. They just randomly pick many different initial conditions, and they assign a color to each trajectory. The advantage is that you can see whether the colors are sort of separated, and then it's a regular dynamics, or close to regular dynamics, or all the colors mix up, and then you see that it's more chaotic. So that's I mean, you could also do it write it in black and white. It's easier to follow the trajectories when you see the different colors. That's it. Okay, thanks for Pauline. So I mean, this is really some very basic physical example. So I advise you to have a look at it. Maybe you can just have a look at the Wikipedia page. Okay, so this is an example of a chaotic system. Actually, this is actually even better. This is just really the transition between integrable and chaotic. It's not really integrable, but it's sort of somewhere in between. It's not fully chaotic. There is a region that is partially chaotic and then fully chaotic. Okay, good. So this is, I'm giving you 1, 2, 3 examples. All these examples were for a single particle. Okay, so this was a single particle. Now let's consider, and there is a reason why I'm going to consider this one. Let's consider now two particles. Two particles. So basically, two particles, you can think of it either as two particles in one dimension or as one particle in two dimensions. Okay, and here one example of integrable versus chaotic dynamics is the square billiard. Square billiard. And so this would be an example of an integrable system. And the other example, let's say an elliptic billiard. This would be an example of a chaotic system. So what we have in mind here is, so what is a square billiard? It could be a rectangular billiard. This is just a billiard. So there is a particle, it starts with some velocity, and then when it hits one of the edges of the billiard, will be reflected using this the regular, if it will use the regular angles, and then goes on more and more. And so in principle, this system is a system with has 4 degrees of freedom. And if you consider only the energy as a conserved quantity, there is just only one conserved quantity. So this is not enough to retain integrability, and hence this will be a chaotic system. However, the square billiard is a specific case in which, in addition to the conservation of energy, you also have the conservation of momentum. Why? Well, there are forces, right? When you hit the edge, there are forces. So the momentum is not really conserved, but the reflection is such that the momentum is just a mirror, it's just flip sign, right? You get in. So if you arrive with some px py, you are reflected with say same px at minus py. The momentum, so the momentum in the x coordinate is constant, and the momentum in the y coordinate is just flipped. So I would say the momentum in absolute value, if you want the momentum squared in x direction and the momentum squared in the y direction, are conserved quantities. In other words, what happens for a square billiard is that you can disconnect, you can decouple the dynamics in the x direction and the y direction. So it's like obtaining two separate particles, in the x and y direction, and then it comes back to the case of just one particle with two coordinates, x and p, and one conserved quantity, the energy, and hence this is an integrable system. So if you want, the square billiard is just the sum of two independent one-dimensional systems. Clear? Okay. So what is, in the case of the elliptic billiard, this is not anymore the case, because in the elliptic billiard, what will happen is that the x and p coordinate talk to each other, because you come with some momentum in momentum x, but the reflection is determined by the place where you hit. So you see now that the x and p coordinate are coupled together, and therefore you obtain a system with, say, 4 coordinates, which is px, py, x, and p, and there is just one conserved quantity, the energy, and therefore this leads to a chaotic dynamics. And chaotic dynamics, as we discussed, it means that if you start from two positions that are close by, so you take two positions, two initial conditions that are very close by, and you will see that one initial condition, say, follow this red path, something like this, let's say, and the other initial condition, okay, the other initial condition will follow initially a slightly different path, but then it will become farther and farther apart. I hope I got it the same right. So although the initial conditions were very close by, actually they separate more and more as a function of time. And if you wait long enough, then you will see that actually you just cannot predict where the particle will be, right? It's if you wait long enough, then you go so far from the initial conditions that there is no clear way to know a priori where the system is going to be. So eventually, this is also an example of a system that is ergodic. Okay, ergodic. What does it mean? Ergodic means that you eventually, independently for any initial conditions, you eventually fill in the whole phase space. You cover the whole phase space for any given initial conditions. Okay, that's this is an example. So it's really sort of an extreme case of chaos, where not only you don't know where you are, but you actually are going to cover the entire phase space. Okay, the reason I wanted to give this example is that this system has a particular property which is called scars. So what does it mean? Scars, actually, I'm not really sure why this name was given. Maybe we can Google it up in the break. But the idea of scars, roughly speaking, the key idea of scars is that it is true that for generic initial conditions, you end up filling in the whole phase space, but there are some initial conditions for which the system remains sort of fixed. It does not. There are some exceptions. Okay, so there are some exceptions. For instance, think of the situation where you start from the bottom and you go straight up. Then, well, what will happen? You will just come back with exactly the same angle. Think about starting exactly in the bottom. You exactly go up. You hit 180 degrees. You come back, and so on and so forth. So this is a specific initial condition for which you do not cover the entire phase space. Okay, so that's that's the exception to the rule. Of course, there are very few such trajectories. I think maybe very few such trajectories. And by the way, if you remember when we saw the kick rotor, you have seen that even in the chaotic case, sometimes there are some sort of islands, like there is a chaotic region and there are small islands, and these small islands are related to these scars. So this is also essentially the same idea, that although the system is overall chaotic, there may be some regions where the system is still regular, or maybe some specific path for which the system is regular. And this is going to be important for the experiment that I'm going to discuss. So the experiment that we are going to discuss is an experiment of a quantum scar. So it's a system that is chaotic. It's a quantum system that is chaotic, but there are some particular initial conditions, some particular, in that case, some particular eigenstates for which the system actually behaves differently. Okay, so we have seen, one particle. So this was a single particle. We have seen two particles, and as you know, 1 to infinity. So we are now going to deal with system with an infinite number of degrees of freedom. Okay, so infinite number of DOF, degrees of freedom. So in particular, let me consider Hamiltonian systems. So a system for which the energy is a conserved quantity. So there is, let's assume that there is energy conservation. And so you have one conserved quantity, but you have an infinite number of degrees of freedom. So that immediately implies that the system is going to be chaotic. And the question that then people ask is, if the system is chaotic, but there is one conserved quantity, how can I characterize the system? And in particular, let's assume that I start from some initial conditions and I follow that path. I follow that path and I say, let's say the system is ergodic. So actually, I'm going to explore the entire phase space. And then the question is, can I obtain so this is for one initial condition. Now let's consider an ensemble of initial conditions. So you now have an ensemble of initial conditions, and these initial conditions, for each initial condition, you have a different dynamics. And so if you have that ensemble, so some probability of some initial conditions, you end up in another probability as a function of time. And you may ask, what is the condition under which this distribution is constant in time? So given, of course, each point moves from one point to the other, but do I obtain, a steady state, or actually, do I even obtain an equilibrium situation? So equilibrium situation is a situation in which actually the probability of there are no, if you choose any closed path in phase space, you will see that the probability of going on one path or backwards is the same. So there are no net currents in phase space. Okay. So again, the harmonic oscillator is an example. It's a counterexample. You see there are all these rotations in phase space. But in an equilibrium system, that doesn't occur. I mean, all the currents sort of equilibrate. And this is, the topic of statistical mechanics. And people have understood that in such an equilibrium situation can be reached if you have some probability distribution, which is a function of energy itself. Well, it must be a function of energy because energy is the only conserved quantity. So if you want, is the only parameter that in the problem is the energy. Therefore, any equilibrium distribution must be a function of energy because it cannot be a function of the initial conditions. This is forbidden. So it can be only a function of things that are conserved. And in this case, you have the energy. And if you, in addition, add one more condition, let's say the condition of locality. So the condition of locality means that you have a very, very large system, and let's split the system in two parts. And let's assume that in part one, you had energy E1, and in part two, you had energy E2. So the condition of locality means that the probability of being in such a state where the energy on the left is E1 and the energy E2 is E2 is just given by the probability of part one being energy 1 and part 2 being in energy 2. Okay, so meaning that you don't have very long correlations between the system is large enough that you can split it in different parts. And then you see that the only way to satisfy this condition is to assume that the probability distribution was an exponent. So e to some a times e, and the exponent really is required such that if you take E1 plus E2, you exactly get the product of the two probabilities, right? In this case, so e to the E1 plus E2 equals to E1 times E2 E2. So the fact that you can split the system into different parts means that the correct function is an exponent, and of course you all recognize that this is nothing but the Boltzmann distribution, right? So minus beta. So there is some parameter. Of course, there is also normalization factor. Overall, the probability must be 1. But the idea that the probability depends on the exponent, I think, can be derived from this idea of locality, that the system, each part is determined by the energy of that specific part. And what is the energy of a particle that is far apart does not affect what is the behavior of a particle here in place 1. This is one way to obtain the Boltzmann. So this is Gibbs Boltzmann distribution. Okay, nice. And by the way, you also so what I want to mention is that if there are more conserved quantities, so if the only energy is conserved, then you have the Gibbs Boltzmann distribution. If you have more conserved quantity, what you will do something similar. So let's say that there are some let's call them, how do I call them, some Li. So let's say that Li is some conserved quantities, and then and there are many of them. So one could be the energy, the other could be the total momentum, total angular momentum, etc., etc. Then what you do, you follow the same strategy and you build a partition function which is e to the sum over I lambda I Li. So also in this case, if these quantities are again local in a sense, then the correct distribution function will be an exponent. It's just that now it's an exponent of all the different conserved quantities. Okay. By the way, this is, for instance, what you do when you go from the microcanonical to the grand canonical. Actually, so from the canonical to the grand canonical ensemble, right? In the grand canonical ensemble, you allow to exchange particles. So there is another conserved quantity, which is the number of particles, and then you build another. So the correct distribution function, right? It's the free energy is the energy minus PV. So essentially, it's like adding another term to the exponent of this distribution function. Again, I'm going very, very quickly because these are things that you should have learned in the advanced statistical mechanics course. But because I'm going to mention them, I wanted to briefly summarize them. And also, okay, well, that's I don't want to. Now let me actually tell you one small story which is actually relevant to what we are going to see now, which is actually the first numerical experiment ever done on a computer, which is the Fermi-Pasta-Ulam experiment, numerical experiment. So, how many of you have seen have heard about the Fermi-Pasta-Ulam experiment? Anyone? No? Okay. Okay, so Fermi, Pasta, and Ulam, so they were researchers at the Manhattan Project, trying to build an atomic weapon. And for making those complicated calculations, the first computer, the first computer was built, which was able to solve equations very, very rapidly. I mean, of course, now it is very slow with respect to modern computers, but this was the first time that the machine was able to do things faster than humans. You may all have seen this. There is this beautiful movie about, there were these women that were doing, on the German side, women that were doing these classical calculations, by hand. There was like a team of people that were multiplying equations. Do you remember the movie? You know which movie I'm talking about? More almost. Okay, so I'll send you the link. Anyway, so but in the US they had this computer and people got very excited about it. And then probably after the Second World War, there was more time to do other type of calculations. And Fermi, Pasta, Ulam, they said, okay, let's try to address this problem. So let's consider a system that has a conserved quantity. So it was a system of 5 coupled oscillators, so non-linear oscillators. And they wanted to study the ergodicity of such a system. So the idea was, we understand the energy is conserved, but there are so many degrees of freedom. There are 10 degrees of freedom. There are 5 oscillators, so 10 degrees of freedom, and then you should be able to explore the entire phase space of these oscillators. And so let me show you again the result of this experiment. And again, if you are interested, you can Google it up. But I think this is something that people should be aware of. So let me share the screen again. Okay, so this is the figure from the original paper of Fermi, Pasta, and Ulam. What you see here is the result of this first computer. This is the first example of numerical physics. So what they did, there were 5 oscillators, maybe 4, I don't know, and probably 4. So what they did, they assumed that they did the following. They started with all the oscillators in the zero displacement, so 0 momentum and 0 potential energy, and they put all the kinetic energy in 1. So the oscillator 1 was initialized in some excited state. So they just it was displaced from the origin, and these are just nonlinear coupled harmonic oscillators. And then the expectation was that as a function of time, you should basically see thermalization. So like thermalization, what does it mean, thermalization? It means that you should have equipartition. So the energy that was in the first oscillator should spread around all the oscillators. And when you come and measure the kinetic energy, on average, you should see that the kinetic energy of all the oscillators become equal. So when you start at the beginning, when you start the simulation, everything goes nicely in the sense that indeed the kinetic energy of the first oscillator goes down and the other oscillators start growing. You see the kinetic energy of 3 and 4 start growing. But then, when you simulate it longer, so that's why you need a high performance computer for that time, you oscillate it longer, you see that actually it's not thermalizing. I mean, you see that the kinetic energy of it's oscillating, and even, which is really worse, which is really bad, after 160 time units, you see that actually the first oscillator acquires back all the energy. Almost all, it's not all the energy, but almost all the energy have gone back to the first oscillator. And this was really, really puzzling. I mean, this was considered as, it was a big puzzle, and there is a whole literature about this topic, how to explain the Fermi, Pasta, Ulam result. I think eventually, I would say the key, I would say that the main idea eventually was that clearly, if this was an harmonic oscillator, if this was an harmonic then just decoupled harmonic oscillators, then clearly just all the energy would remain in the first oscillator. And what was found is that essentially this system was close to an integrable system. So the system itself is non-integrable. It's non-linear, it's non-integral. But you can, if you want, the non-linearity is weak, okay? In the sense that this system was close to be integrable, and that's why it behaved similarly to an integrable system. In other words, if you really waited very, very long times, eventually you will see thermalization. You will see that all the energy spreads around the modes, but that will require a lot of time. And the reason is that this is close, it's in a sense close to integrability, okay? So, and it turns out that the thermalization time depends in a very nonlinear way on this closeness to integrability. So again, if you aren't integrability, then there is no thermalization at all, forever. The system is not ergodic. If you are close to integrability, then the thermalization may require a lot of time. Okay, that was the main finding. Okay, good. So this was the review of classical physics, and now, so A, classical physics, B, something about quantum systems, B, quantum systems, quantum chaos. So first of all, there is a huge problem. Let me, first start the problem. The problem is that, as you all know, Schrödinger equation is a linear differential equation. Right? It's a linear equation of time. So it automatically means that it's an integrable system. And indeed, if you just want to evaluate the time evolution of the system, the time evolution is simply sum over I, Ci e to the minus ei t times phi I. So once you diagonalize the Hamiltonian, the time evolution is very simple. And as a function of time, there is always an infinite number of conserved quantities, which are the prefactors of the state with respect to the eigenstate in the basis. So if you work in the basis of the Hamiltonian, then these prefactors are conserved quantities. They're always the same. Take them square if you want, and you see that in other words, psi of t, phi I. So phi I, these are the eigenvalues. Okay, eigenstates. EI are the eigenvalues. And if you project the state on phi I and square it, this is a constant. This is a constant, and it's a constant for any. So there are 2 to the n eigenstates. There are some number of eigenstates, and you have the same number of conserved quantities. So clearly, this is an integrable system. However, this is a bit strange because we know that physically systems can be integrable, non-integrable. So the question is how you even define a system that is quantum chaotic. And again, there are different ways to define quantum chaos. Let me follow one way, which is sort of a mainstream method. And the mainstream method says, well, consider a system that is quantum chaotic, but let's not observe these quantities. Let's forget that we can really project the state on these eigenstates, but let's focus on physical observables. So clearly this is not an observable, right? This is not a local physical observable. This is a very complex object. But let's now think of having, say, a system of spins, and then we compute, say, the magnetization of each spin, and we can define quantum chaos according, or maybe thermalization, according to the question whether if you wait long enough, then the observables, there will be, say, equipartition, or for instance, whether you can ask whether, say, sigma z I is equals or not to trace of sigma z rho thermal, where rho thermal is some e to the minus beta h Hamiltonian. Okay, so the question is, if I wait long enough, so I initialize my system in some state, I wait long enough, I take t that goes to infinity, and ask myself, do I obtain a thermal ensemble? Forget about the states. I don't want to diagonalize the Hamiltonian. I don't want to know the density matrix. I just want to measure physical observables and ask whether these physical observables are the same as a thermal ensemble. And this would be a system that I would call chaotic or thermalizing. And again, you can see that, and the statement is, in analogy to the classical statement, is that if you have enough classical variables, if the number of degrees of freedom is large enough, then you can always, this will always occur. Okay, so this is basically an assumption which seems to work very nicely. The assumption is called ETH, or eigenstate thermalization hypothesis. And it basically tells you that if you start from some initial conditions, then you end up, irrespective of the initial conditions, you eventually end up in some thermal state with some temperature, and temperature is determined. So the only conserved quantity is the energy. So temperature will be determined by the initial conditions. But rather than that, there are, it's just like a thermal ensemble. Why it's called eigenstate thermalization hypothesis? You see this first word, because in order to have this assumption, you need essentially to assume that each eigenstate behaves as a thermal state. Okay. Otherwise, remember that when you do the time evolution, you are just evolving in some basis of eigenstates. So in order for the system to behave thermally, you actually need that each of the eigenstate behaves thermally. If you want, this is a necessary condition. At least you need the eigenstates to behave thermally. And again, this is a problem that has been studied a lot in the literature. But what was observed on a broadly speaking, is that whenever you take an Hamiltonian that is complicated enough, so generic Hamiltonian, what you will see is that when you observe, say, again, you take sigma zi in some eigenstate, okay, you will see that this equals to trace of sigma zi rho thermal, where again, the temperature depends on the eigenstate. So when you choose a different eigenstate, the eigenstate sits at the given energy. So that energy fixes the associated temperature. And what you generically observe is that the sigma zi behaves as a thermal behavior. Let me just explain one more concept which is associated with this observation, is that what you are doing essentially, you're looking at a local observable, right? Sigma zi is a local observable. What does it mean? When you compute the expectation value of that observable, you are essentially averaging over the entire system, right? You are tracing out the rest of the system, because you take the wave function of the whole system, and then there is an operator that computes an expectation value on a given state. So you are essentially integrating out over the rest of the system. You are averaging over the rest of the system. And then the rest of the system essentially behaves as a thermal buff. So it is as if your spin was coupled to a thermal buff. The rest of the system behaves as a buff. Okay. So this idea of eigenstate thermalization is related to the question, to the idea that, the rest of the system behaves as a buff. And now we don't really have enough time to go into the details, but the idea is that starting from the eigenstate thermalization hypothesis. So if you assume that the eigenstates behave thermally, then you can get to some thermalization behavior. So even if you start from a superposition of eigenstates, then you can, again, you need more conditions, but you will end up also with a thermal state. But I think the first condition to require is that you need the eigenstates at least to behave as a thermal. So not that the eigenstates themselves, are eigenstates. They are not thermal states. But the idea is that when you look at local observables in an eigenstate, this behaves as a thermal, as a thermal ensemble. That's the idea. And when this holds, then you can have thermalization. So this is a necessary condition for thermalization. Okay, questions. This was really, really fast, so feel free to ask questions. No? Okay, so let me just repeat this point because this is it's not trivial. So what I've said two things. The first thing is that if you start in an eigenstate, the time evolution is trivial. It's just it's like an harmonic oscillator, right? E to the minus I et, just an harmonic oscillator. So if you take an eigenstate and you study the dynamics, it's just a phase. It's a equivalent phase. So there is no thermalization. It's just a boring oscillation. If you start in a superposition of eigenstate, that each eigenstate rotates with a given given frequency. So this is an example. Schrödinger equation is an example of a linear system and it's integrable. That's true, but the problem is, so how do you define thermalization? How can you observe a thermalization? And the answer is, in order to observe thermalization, you need not to look at the eigenstate itself, not to look at the state of the full system, but rather at the subsystem. So you take a full system, but you measure a local quantity. Local quantity could also be a sum of local quantities. This is still a local quantity. As long as I don't really probe the entire wave function of the whole system, but I just look at, say, a sum of local terms, that's fine. And then the idea of thermalization is that probably, the eigenstate itself, the whole system is not thermalizing, it's just in a given eigenstate, let's assume. But when I look at the physical observable, this physical observable will have an expectation value that is similar to a terminal state. Again, this is an assumption. It's called eigenstate thermalization hypothesis. And the assumption is based on the idea that when you look at local observables, you are integrating out the rest of the system. And when you do that, the rest of the system essentially behaves as a thermal buff for the system itself. So as if you had a small quantum system coupled to a huge thermal buff. And again, this is just an hypothesis. It turns out that it works nicely. It works very, very nicely. So nicely that when you see an exception to that, you're very surprised. Okay, and this is what I would like to discuss with you today. So the experiment that we are going to discuss today is an experiment that was, you can really think of it as the quantum Fermi-Pastor-Ulam experiment. So it was an experiment that was meant to demonstrate, say, thermalization, and instead they didn't see thermalization. Okay, questions? Okay, so what I would like to discuss today, this is really the main topic, is exceptions to ETH, to eigenstate thermalization hypothesis. Situations in which the system does not thermalize. So one example is just decoupled spins, say. If you have just spins, many spins, as many as you wish, but they're decoupled. So each of them just rotates. There is no thermalization. It's quite obvious. It's related to the fact that the spins are decoupled from each other, so they cannot act as a buff one from the other because they just sit there and they are decoupled. By the way, for those of you who know the transverse serializing model, this is an example of such a system. The transverse serializing model is not really decoupled spins, but when you can move to a basis in which these are decoupled spins. When you move to momentum space, you actually obtain decoupled spins. Again, for those of you who haven't met the transverse serializing model, then fine. But for those of you who have, then this is an example of an integrable system. So clearly, if the system is integrable, there are many conserved quantities. They are decoupled spins. It's integrable. Second example, it's actually something that we have seen in one of the previous lecture, which is MBL, many body localization. So this is a quantum system that is not decoupled, but it has a lot of disorder. And what people were able to understand is that when there is a lot of disorder, remember in analogy to Anderson localization, so Anderson localization is for a system of interacting particles. And what you see is that the eigenstates are localized. And so when the eigenstates are localized, you can really think of each of the particles as independent from the other because each of them is localized. Again, this is highly non-trivial, but it turns out that this many-body localized system can be effectively written as some effective degree of freedom that are decoupled one from each other. And again, it's related to the idea of localization. So if you have delocalization, that all the degrees of freedom talk to each other. But when you have disorder and localization, essentially each local degree of freedom becomes decoupled from another degree of freedom at different position. You know, for each place you have like a local degree of freedom that becomes decoupled from the rest. And so this is also an exception of ETH, but these two are sort of together. These are something that it's quite obvious that it should not be ETH because it's like examples of integrable systems. So of course they are not chaotic. And now comes another example, and this is the example that was more of a surprise. And this is a system of Rydberg atom. And the system, we are going to discuss in more details the experiment, but for the moment, think of Rydberg atoms as just as two-level systems. So there are many two-level systems. Okay, each of them is a two-level system. So what you do, okay, these are Rydberg atoms, and what happens for Rydberg atoms is that actually they have some coupling between them, and the coupling is such that if say the state 1 is in excited state, let's say if this is 1, this is 2, okay? So the idea is that if 1 is excited, then the level splitting of 2 is affected, okay? So these are basically, each of these two-level systems is a dipole, and the idea is that when you create a dipole on state 1, you affect the dipole. So if the atom 1 has a dipole, there is a dipole in the atom 1, this will create some effective dipole or some effective electric field for the atom 2, which will shift the level splitting. And the experiment was performed as follows. So it was, and this effect is called Rydberg blockade. We are going to see more details in the sort of the experimental part. What you need to know from now is that you can think of so what you do, you drive the system with some sigma x. So you drive a Rabi oscillation between up and down. It's like applying a magnetic field in the x direction, so that you know that if there is a two-level system, you apply the magnetic field in the x direction. So you are in the Bloch sphere, you point down, and then you start rotating. This is just a standard two-level system that you apply magnetic field in the x direction. You observe rotation, so you go from down to up to down, etc. So you apply the same field for all the atoms. So in principle, let's say that all the atoms started down, they should start rotating all at the same frequency. But there is a problem. What is the problem? The problem is that if atom 1 is excited, it goes up, then the level splitting of atom 2 is shifted, because as we discussed, there is some interaction between them. And hence, when the level splitting is different, the Rabi oscillations is blocked. In order to obtain Rabi oscillation, you need to excite the system exactly on resonance or close to resonance. That's the way to obtain those rotations. And so if the atom 1 is excited, the atom 2 now is not more in resonance because you shifted the energy splitting, and so it cannot rotate anymore. That's basically the idea. And so there is the process is defined by Simon Hamiltonian, and so the Hamiltonian, let me write it. It's now it became very famous since the experiment. It's called the PXP Hamiltonian. PXP Hamiltonian, I plus 1, I plus 2. Sorry, PXP, PXP. So X is the rotation, okay? This is the rotation of the atom I. Actually, let me define as follows. Let me write it as, it's the same. So let me write it, Pi minus 1, Xi, Pi plus 1. So this is the rotation of atom I. Okay, so if I just had Xi, this would be just a rotation of the atom I from down to up, right? This is what X does for us. What is Pi plus 1 and Pi plus minus 1? So this is a projection that demands, basically, these two operators demand that the atom I minus 1 and the atom I plus 1 are de-excited, are in the ground state. Okay, so this is one. So basically Pi plus 1 is 1 if I is in the ground state, I plus 1 is in ground state, and 0 if I plus 1 is in excited state. Okay, so this is something that the idea is that if I'm looking at the atom I can rotate only if both the atom on the left and on the right are be excited. Because then I am exactly on resonance. If the atom that is sit to my left or the atom that sit on the right are excited, then I cannot. Then I am out of resonance and I cannot rotate anymore. Okay, so of course this is an approximation of the whole physics, but an approximation that works very nicely. Okay, this effect is also known as Rydberg blockade. What does it mean? So again, Rydberg blockade means that if an atom on the right or an atom on the left, actually if an atom that sits within some distance, which is known as the Rydberg radius. So if I have atoms that are excited, that are close by, then I get off resonance and I cannot be excited anymore. Okay, so you can also write, of course, pi plus 1. You can write it as 1/2 1 minus zi plus 1. So again, if z is plus 1, then this gives you 0. This is exactly the same, right? It's just a mathematical form of writing 0 if you are excited and 1 if you're in the ground state. So you see that actually, if you open up this parenthesis, so you can take this and you can take the p, substitute in the Hamiltonian, you will see that you will obtain some Hamiltonian that looks like a Ising model. So there is like zxz, some z terms, there are all sorts of terms. Okay, very nice. So this is a Hamiltonian. This is the Hamiltonian that is non-integrable. So naively, one would expect this Hamiltonian to be thermalizing. However, when they actually did the experiment, they observed some magnetization. Again, we'll see the experiment in detail, but essentially they probed, let's say, sigma zi, magnetization. And if for a system that thermalizes, the expectation was something like this. So maybe some oscillation, but eventually the magnetization should go to 0. Why? Because, well, at least it should go to a constant, Let's not commit to 0, but it should go to a constant. Actually, for all the spins, it should go to the same constant. So maybe there was another spin that was started down, and this should, they should approximately go to the same constant. May take some time, but this was the expectation, thermalization. Instead, this is not what was observed. So what was observed in the experiment was basically something like this. So there were oscillations, the spin would oscillate between 0 and 1, and it didn't seem to thermalize. And what they did, they actually did both the experiment and they said maybe something is wrong with the experiment. So they actually also computed the evolution of the Hamiltonian, just the theoretical evolution of the Hamiltonian, and it also gives the same evolution. So it's really something special about this Hamiltonian. And basically, and the question was, what's so special about this Hamiltonian? It's non-integrable. So, this is clear. And there were two possible explanations that were followed. I'm now summarizing. So the two possible explanations, which are sort of related to each other, but not quite. So there are two possible ways to explain this. Yes.
Can I have a question?
Yes, please.
So in the experimental graph, so what we see, right, is just a rotation. It's like we're applying X all the time.
Yes, but this is about square root of 3 sigma x, but not quite. Maybe actually it's 1.5 sigma x. Sorry, 1.5. I mean, the frequency of this oscillation is not the oscillation of a single sigma x. It's a multiple of sigma x. It's if you just had the decoupled, what I'm trying to say, if you just had the decoupled spins, you're right, you would just see oscillations. But the frequency of the oscillations that you see here is not the same as the frequency of the oscillation of the single spin. So the Hamiltonian does play a role.
Yeah, okay. So because it was weird because it seems like it's like decoupled and
exactly. So it's not. And first of all, it's not because the Hamiltonian. So what I'm saying is that first of all, the Hamiltonian is important. It's not just decoupled rotation of this oscillator because the frequency is not the one you would expect. It's like 50% higher. So it's a different effect. The Hamiltonian is important. Point number one. And point number two is that this Hamiltonian cannot be written as a sum of decoupled oscillators. I mean, maybe it can, well, it cannot actually. People really, actually, there are ways, given an Hamiltonian, there are ways to discuss whether it's thermalizing or not.
I just thought, that the experimental results is, okay, you think that you have this Hamiltonian, but maybe you just have, decoupled.
Very good. So this is a very important question. That's why in the paper, by the way, I'm going to give you the reference in a moment. In the paper, they also did the numerical evolution of the PXP model. And they saw that it really fits very nicely the experiment. So it's not a bug in the experiment. And the frequency was this, 1.5 was the same 1.5 in the theory. So it's really, it's really something about the physics. Okay, it's not just something wrong with the experiment. Okay, so there were two possible ways, and I put all the references in the lecture notes, so you will see there. But I would say there are two possible strategies how to solve this, and in a sense they both work. How to explain this behavior? So the point number one is something analogous to what I said about the Fermi-Pastaula, which is to say, well, maybe that, so this is called the Hamiltonian is called PXP. So maybe PXP is not integrable. We all agree, but maybe PXP is close to be integrable. What does it mean? Maybe I can add some perturbation and obtain a Hamiltonian that is integrable. Okay, so it's close to integrability. And the first, there were different groups. Well, this was a very highlight 2 years ago, and there were many groups working on the same topic. So one group just did numerics. So they said, let's consider the Hamiltonian PXP. Let's add all the perturbations that preserve the symmetries of the Hamiltonian. There are some symmetries. And they just studied numerically, and they saw that by playing with these factors, they were able to make it more and more integrable. So they added more terms to the Hamiltonian. They consider, say, PXP plus some perturbation, lambda IVI. So they added many different perturbations, and they played around with the perturbations, and they saw that by adding these perturbations, they become closer and closer to integrable. And so probably they assume that if you add an infinite number of perturbations, but they're small. So this is the point, okay? This is 0.05, I don't know, this is a small number. So by adding small perturbations, you can make it integrable. So that's approach number one. Approach number two is more around the direction of the scars. So let's say quantum scars. So remember what we had. So what was a scar? A scar said, well, you remember it came from the elliptic billiard. You say, well, the elliptic billiard is non-integrable. Okay, fine. But there are some specific states that are integrable, that are very simple. You remember this going up and down. The up and down is, well, the whole phase space is non-integrable. There are specific states that and maybe by chance, actually the state that they began with was close to this state. Or in other words, there was a large overlap between the initial state and this quantum scars state. So at the beginning, these quantum scars were written sort of phenomenologically. Then later on, actually, people were able to use a tool that is known as MPS, matrix product states. Again, probably Yoni, you heard about it. You may have heard about it. So it's a method to just write down quantum states in a convenient manner. I mean, right? You need to write down a many-body quantum state. So it's a huge wave vector, and you can write it very compactly using these matrix product states. And so they were able to show that indeed there is such a state that is integrable, for which the Hamiltonian that is very simple. And it's a very simple eigenstate of the Hamiltonian. It's not the full spectrum. I mean, the full spectrum is very complex states, but there are few eigenstates that are peculiar. And these quantum and in addition, the initial state that was considered in the experiment had a large overlap with the matrix product state. Okay, so that's what you need these two conditions. Okay, that's enough for the theory part. So unless there are questions, we'll take a 5 minutes technical break, after which I'm going to move to the experimental part. And actually for the experiment, I'm going to show you a movie of a recorded presentation that we had here at the virtual presentation that we had at the Department of Physics a couple of weeks ago, which I think was given by one of the people working on the experiment. And I really liked it a lot. I think this is very, it's very instructive. He explains about the experiment. He shows about these quantum scars, and it's the right length. He spoke also about other topics, which I'm going to skip. If there are questions, we can stop and comment. But I think I like his presentation, so we are going to watch together at the presentation. So questions? No? Okay, so then let's take, very, very short break. So we'll meet again at 11:15, and I'm going to show you, I'm going to open this movie, and we're going to watch it together. So let's go back to the presentation. Well, okay, the guys in the physical room, they're still not here. Okay, but it's time. So what I'm going to present now is a part of the presentation given by Sepper Ebadi from the Harvard group. The Harvard group led by Misha Lukin was the group that did this experiment that I was mentioning to you. And so we are going to watch together this the presentation that he gave to the system. And I think.
And lastly, superconducting qubits have been able to show quantum advantage over classical computers with only 53 qubits when they sample random unitary circuits. And in this talk, I actually will focus on Rydberg atom arrays. And let's first see what features of these devices make them so attractive. Firstly, they're highly scalable. We can create very easily defect-free arrays of these neutral atoms with up to, as I will show in this talk, 256 qubits, and recently we've done work with more. They offer competitive fidelity and coherence in the operations. They're incredibly tunable. We can change the geometry of the system, the interactions, literally with a touch of a button. And also, because of the way these systems are implemented, as you will see, local probing and readout comes for free. Essentially, you can do microscopy without doing any extra work. And lastly, compared to most atomic physics experiments, these experiments have very, very fast cycle times. And we operate usually around a 3 Hertz cycle time, so you can get a realization of the experiment at a rate like that. The main working principle behind these atom arrays is essentially assembling them and removing the entropy from them by observation, something similar to what Maxwell dreamed of with his demon. We first create a tightly focused laser beam, and we overlay that with a magneto-optical trap. If this laser beam is so tightly focused, or namely the optical tweezer is so tightly focused, it can only host one atom. Now, if we have many of these tweezers in our vacuum chamber, we can see that with roughly 50% probability, some of them get filled and some of them are empty. We can then image these and remove the tweezers that were empty, then rearrange the remaining traps to create a regular atom array. And now we've ended up with a defect-free initialization point of the system. And now the challenge is to how can we go and engineer the interaction between these atoms and study many-body physics. I will describe later, and we do so by exciting these atoms to the highly excited Rydberg state and utilizing the dipole-dipole interaction between these to realize many-body physics. The outline of this talk will be, first, I will tell you about programmable two-dimensional arrays of Rydberg atoms. Then we will look at quantum phases and phase transitions on square arrays of Rydberg atoms. And lastly,
we'll see that we'll watch the introduction, and then we'll.
And lastly, we will discuss quantum many-body dynamics of quantum scars in these systems. So first, let's focus on how these two-dimensional arrays are created. The device that allows us to create these two-dimensional array is called a spatial light modulator. It's actually not very different from the liquid crystal LCD display from which you're looking at me right now. This device is a chip roughly the size of a few centimeters, and it has many pixels that are made of liquid crystals. And this allows us to take an incoming beam, shine it on this display, and then change the wavefront of it. For example, if we display a tilted slope on this liquid crystal display, this SLM, we can steer the beam into different directions. And using very well-known techniques in holography, we can create a hologram on this device that allows us to take a single beam of light and turn it into many, many different beams that are pointing into different directions. And then when we focus these beams of light, we can actually create many, many optical tweezers. Here, I'm showing you a picture of 1,500 optical tweezers formed using this technique with a high degree of homogeneity and
optical squeezers is a topic that we discussed earlier.
Efficiency. We then image these optical tweezers onto our vacuum chamber, and inside this vacuum chamber, we can create these cold clouds of rubidium and trap the atoms. And on the other side, we have another microscope objective, and we can then image the atoms on a CCD camera and also have another camera to monitor the traps. If we run the experiment, if we, for example, have a tweezer array that looks like this, then in real time, this is what you would see. Each dot here corresponds to an atom, and you can see that about 50% of the traps are filled after each step of loading. Now the question is, can we actually go and rearrange the atoms so that we can fill a subset of these traps with very high fidelity? And to do so, we need another device because the spatial light modulator is actually kind of slow in moving tweezers and it's not flexible enough. We add another set of optical devices, namely the acousto-optical deflectors, which allow us to turn an electrical signal into a beam pointing of the device. We then take a beam of light going through these acousto-optical deflectors. We focus them on and overlay them with the tweezers that are generated by the SLM. And using it, after we image the atoms, using the arbitrary waveform generator, we broadcast a sequence of pulses that pick the atoms up and move them into their final position. Pictorially, this would look like the following. For example, we turn on if we have loaded this arrangement of tweezers with the atoms being the black dots, we can turn on the AOD tweezers, which are much deeper than the SLM tweezers. We essentially turn them on, pick the atoms up, move them to their final destination, and drop them. And we can do so in parallel, actually. As we sweep up, we can turn on different tweezers and pick up an atom and move them to their final destination. And this is an animation of what actually happens in the experiment in about 100 milliseconds. And we can move the atoms to their final destination and end up with a visualization of our system. If this is our initial loading, after a round of rearrangement, this is the result that we get. You can see that the excess atoms are pushed to the bottoms, and the top is filled with very high filling factor. And this is, again, what it would look like if you ran the experiment in real time. We have about 99% filling in the target sites that we have. And this means that we actually have a substantial probability of starting with a perfect array that we want. So in a lot of our experiments, we post-select on having had started with the perfect array. And sometimes you don't even need to post-select, and you can tolerate some amount of error.
Seper?
Yes.
So you keep mentioning this.
For example, move from the reservoir to a set of a square lattice. So this is what we do when we can have a little bit of fun. So far what I've shown you is atoms in the ground states. They don't interact yet. So how can we actually go and start making them interact? We excite the atoms to the Rydberg state. A Rydberg state is a highly excited state of an atom. So for example, in the case of our work, we work with rubidium atoms. In the ground state, they're roughly 100 picometers in size. And when we excite them to the Rydberg state, in our case, the principal quantum number is 70, you can see that the size of this atom becomes gigantic. They become a few hundred nanometers or sometimes a micron in size. We excite the atoms using 2 photon transitions for the expert in the audience, meaning that we first, because this energy is so large that you can do it with a single photon, but it's not very easy. We first go to an intermediate state and then go to our final Rydberg state. And for the purposes of this talk, you can ignore the fact that there is 2 photons and essentially think of it as a 2-level system with a drive term, like a sigma x term, and a detuning term, which you can think of as a sigma z, n being the projector onto the Rydberg state. And what do we do as physicists when we have a 2-level system and this Hamiltonian? We drive Rabi oscillations. And here we can see that we can drive Rabi oscillations for many, many cycles with a fairly high Rabi frequency before seeing any sign, any visible sign of dephasing. And now what happens if we add one more atom to the mix? We actually get one more term in our Hamiltonian, which is the interaction between the atoms. The atoms interact when both of them are in the Rydberg state. So this plot essentially shows you that when we have 2 atoms in the ground state, they do not interact as a function of distance between them. When you have also 1 atom in the Rydberg state, there's no interaction between a ground state atom and a Rydberg state. However, when you have 2 Rydberg atoms, as they get closer to each other, the interaction energy between them pushes this energy up. And at some point, for some distance between these atoms, this interaction energy is so large, and we call this point the blockade radius. At this blockade radius, the interaction energy is so large, and it's in fact larger than the Rabi frequency. And this means that you cannot have both atoms excited to the Rydberg state. So if you have a Rydberg state and another atom within this blockade radius, you cannot excite this on resonance. And this blockade, Rydberg blockade, is actually the fundamental process that allows us to study a lot of the physics that we do. So with that, I wanted to conclude the section on the programmable Rydberg arrays. If there's, maybe if there are questions.
Okay, good. So this is the introduction. I think he sort of reviewed things that we have seen together, just more accurately. And now we are going to skip here to the part that speaks about the scars. So it's about minute 84. Okay, good.
I also want to bring you to your attention by to the work in Antoine Brouet's group in Paris, that they've done fantastic work understanding and benchmarking the checkerboard phase in a system very similar to us as well. And this brings us to the last section of the talk on quantum many-body dynamics and scars. So here I will deviate a little bit from the theme that so far that you saw is, with the exception of the striated phase, everything essentially was static. We were trying to look at systems somewhat in equilibrium. However, in this case, we want to look at dynamics in these systems. For example, we can start by asking the question of what is quantum thermalization? We can think of, we prepare this many-body state in a pure state. The entire system is in a pure state, and if you look at a local observable, it, for example, will not look thermal. However, let's say we hit the system with hammer and it undergoes unitary dynamics, it's still decoupled from the environment. The many-body system is still pure. However, if you look at local observables, they start to look thermal. So, and this is very beautifully phrased as the eigenstate thermalization hypothesis that tells you that local observables after some unitary evolution go to their microcanonical predictions and stay there. However, there are certain classes of states and systems that actually break this generic behavior. You've probably heard of, for example, many-body localization is an example, but in this work, I will tell you about quantum scars. They were first observed in a 1D system in a previous version in our experiment by first preparing a one-dimensional checkerboard phase. Here, on the top, I'm showing you the detuning profile to go from negative to positive to prepare this phase. And on the bottom, I'm showing you at different snapshots along this sweep. You can each vertical column corresponds to the atom position. So there's 9 atoms in this chain, and you can see that after the preparation of the phase, you have a one-dimensional checkerboard phase. You have Rydberg ground, Rydberg ground, Rydberg ground. And now,
okay, so this is the initial state of the experiment. The initial state, they prepare this 0, 1, 0, 1, 0, 1 state.
You quench the system on resonance. You would expect that because of just dynamics, it would essentially quickly look messy and start thermalizing. However, it was observed that after this quench, the system undergoes these oscillations for quite a while. So the system is oscillating between one checkerboard state and the other checkerboard state, the odd and...
Okay, so it's basically oscillating between 0, 1, 0, 1, 0, 1 and 1, 0, 1, 0, 1, 0. You see, as a function of time, here at this point it says 0, 1, 0, 1, and here it's 1, 0, 1, 0, and so on and so forth. And the plot that I was showing you is, okay, this is a color map, but you can see that basically it goes, if you take a fixed qubit, you will see that it goes up and down, up and down, up and down for relatively long times.
This was observed in 2017, and it was very surprising that how the system thermalizes so slowly. This inspired a new theoretical concept, this quantum many-body scars, and it was shown that there's these special scar states that follow under this quench Hamiltonian, follow a very specific trajectory in the Hilbert space and oscillate back and forth. There was also beautiful work that showed that there's a very nice MPS representation of this process. And there's, of course, many, many other theoretical work that was inspired by this one. So maybe quickly we can see that why these quantum many-body scars appear in 1D by showing you that if we have this Hamiltonian and we prepare this checkerboard state, when we do the quench, actually we can approximate this Hamiltonian with another Hamiltonian called the PXP Hamiltonian. PXP is essentially another fancy way of saying, for every atom, look to the atom in the right and the atom on the left, and if they were both in the ground state, you can apply the X. This essentially assumes perfect blockade, meaning that no 2 atoms next to each other can be excited to the Rydberg state at the same time. So now if we start with this system in the checkerboard phase and apply the PXP once, we can see that we couple to these states. For example, if we apply PXP on the atom to the left, it gets excited, and if you apply it to any other atom, it cannot excite an atom. And so on and so forth. You can keep applying the PXP, and you can see that there's this insane network of coupling of all of these states. However, all of these trajectories at the end interfere to give you the state that is the opposite checkerboard state. So here you started with Rydberg ground, here you have ground Rydberg. So this is the intuition behind why certain eigenstates have this scarred behavior and they oscillate back and forth. So it was not very clear whether this scarring behavior would actually exist in 2 dimensions. So we just decided to do the experiment, and the experiment is very simple.
Okay, So I propose that we stop the presentation here. Again, in the lecture notes, you will see the link to the presentation itself. So if you're interested, you can watch the continuation, you know, where they actually study the problem in 2D. I think now, in the interest of time, it's time for us to conclude the experimental part of the lecture. I think we have a presentation by a student today. Itamar?
Yes.
Okay.
Yeah.
So do you have it on the computer or?
Yeah, but I think we need like a few minutes to arrange things here.
Okay, sure. So, you know, when you're ready, just give a sign and start.
Okay.
Take your time, and when you're ready, we can start.
יש לך דיסק-און-קי משהו?
לא, יש את המחשב שלי,
שלח לעצמך.
ויש לי, אני יכול פה, אבל אין פה, יש פה אינטרנט?
יש פה אינטרנט.
אז יש את זה בדרייב. יש פה אבל זה.
אני גנבתי, כן. תביא כיסא.
Okay, can I share the screen? Sure. Okay. Good, nice. So can you hear me and see the presentation?
Yes, Itamar, please go ahead. So I apologize if at some point I will need to go to without video, but I will be still following. So Itamar, please go ahead.
Yeah, sure. Okay, so thanks. I'm Itamar. I'm going to present here. This is basically some version of my research proposal, and it's focused on superconducting flux qubits and how to couple them with another quantum system, which is this nano bridge. And basically, we're proposing a way to do a hybrid system that can help us with quantum computation. So, okay, this is my team. I don't think it's really important here. Yes, so let me just do like that. Yeah, okay, so the motivation for this project in general is that we want to have a quantum computer. It will help us to make some computational tasks that are predicted to be very difficult for classic computer and etc. And I think everybody here knows this. But today there are two. You can take the platforms today and kind of divide them into two. So one of them, they have very high performance, what we call, and in performance we mean they live for long times. So they have a long coherence time. For example, this Rydberg atom that we saw, or nuclear spins in diamonds, stuff like that. So they can live, they have coherence of seconds. But the problem, okay, they have this very good coherence because they are very isolated from the environment. So there is nothing that decohere them. But because of that, it's very difficult to control them and to scale them up, because basically if you want to have a computer, you need to interact with it, with the qubits. So these systems nowadays, we can like couple together or work with on number of qubits on the order of 1, 2, etc. On the other hand, we have a very scalable system like superconducting qubits. This is just like microwave components on a chip. It can be on silicon or sapphire, and the fabrication is like lithography that's used in classical computers. So it's very scalable, and you can have, for example, I'm sure everybody heard about the experiment from Google and stuff like that. So you can have up to about 50 qubits today, but they live for a very short time, which is on the microseconds in the good case. So in order to, one way to overcome the obstacles that we have, for example, with these superconducting qubits, we want to like artificially make their life longer, so we can use error correction schemes. So for example, there is the surface codes. I'm not going to elaborate on that, but basically it's a code that uses hundreds of qubits. It's more like a redundant encoding of the information. So like in classical error correction, instead of having just, let's say, one bit that says 1 or 0, I can take 3 identical ones and then do majority vote and decide what is the right answer, even if one of the bits is flipped. So you can go and expand this to also to quantum bits, but then you need like hundreds of physical qubits just to encode one logical 0 and 1. Another way, which I'm going to talk a little bit more here, to do error correction is what is known as bosonic codes. So basically, instead of using a redundant number of physical qubits, you take a different kind of qubit and use redundant Hilbert space. So infinite Hilbert space, so instead of having just a 2-level system, which give you 0 and 1, you can take an harmonic oscillator, which has infinite number of energy levels, and encode your information inside coherent states. So in a moment, I will elaborate more on that. And the way to, so what you see here in this picture, so basically you can, and again, I will go in more details in a second, you can generate a state, which is a superposition of coherent states, and this will be your logical basis, your 0 and 1. And if you take, again, a superposition of this 0 and 1, you can form a closed 4-state set, which will be your basically your computational space. And one way to realize such systems is with what you can see here. This is the superconducting qubit at Ransmon, which is coupled to two resonators. So you see we have here one cavity inside it. This is a macroscopic centimeter or millimeter scale, just 3-dimensional cavity in aluminum. And you see here you have one resonator, which will be the storage, which will be the qubit. There is another readout resonator, and between them we have this Ransmon qubit, which is the nonlinear element, and I will show you in a moment why do we need it. So again, I'm going to talk more and explain more about this scheme. So what you can see here for the bosonic encoding, so basically you can say that your psi, your quantum state, is a superposition of coherent states. And then, okay, let's say that it is like an even with this prefactor here, what is not really important. So this is your state, alpha plus minus alpha. And another thing that's important, that this state is an eigenstate of the parity operator. So it just tells you if you have an even or odd superposition, and this will be important for the realization how to measure the state without collapsing it. So you can just measure its parity, and you know if you're in the plus or the minus without actually measuring the state itself. So one realization of this state is with a Kerr medium, and basically Kerr medium says that you have a nonlinear term which goes like a dagger a squared, or the number of photon inside your system squared. And then, okay, if you just evolve in time your system inside this Kerr medium, you can see here the equation, but I don't think that we really have time to go over all the details. But basically, you can evolve your system. You just begin with a coherent state, and you can get into this superposition. So you need a nonlinear term like this Kerr term. And then you can generate this superposition. And this nonlinear term in this picture that I show you here is the transmon qubit. Okay, so the transmon acts like this Kerr medium. And this is how things like that were realized till now in the Yale group. So for the CAT codes itself, for how we do the error correction, so we have the computational basis. So as I told you, we have the superposition of coherent state. So we have this C alpha, and we have Ci alpha, which is just a phase here, I alpha plus minus I alpha. And we can choose to work in a logical state that 0 is C alpha plus and 1 is Ci alpha plus. And then if we take an initial state to be a superposition of these two, of 0 and 1, we will see that if we apply, if an error syndrome occur, we can track it. And by error syndrome, because we are working with basically harmonic oscillator, which is the qubit, which is this, that give us this coherent state. So the main loss channel is just the photon loss. Okay, so this is what happens in a resonator. You mainly lose photons. And what happens, okay, so if we start with this initial state, psi alpha, and we apply this operator A for photon loss, so we can see here, okay, we apply it once, we are going to another set, another superposition of this C alpha minus, plus I C1 I alpha minus. Okay, the details are not really important, but what I want to emphasize here, okay, we apply it once, we go to some other state. We apply it twice, we go to a third state. We apply it for the third time, we go to a new state, but then if we apply it for the fourth time, we're going back to the initial state. Okay, so overall, if we have such a system and an error syndrome occur, we just move between one of these four states. And all of them are an eigenstates of the parity operator. So basically, if we can measure the parity, just the parity, and I know from which state I started, so if I can have a real-time track on this of the parity, I can detect these photon losses. Because when I go from psi 0 to psi 1, I change the parity. And again, if I go from 1 to 2, I'm going to the previous parity. And this is what is emphasized here in this figure. Okay, so basically we have here a platform that gives us the ability to track errors, and I know exactly at which state I am just if I count the number of photon jumps that I had in the system. So do you have any questions so far? Or?
The reason to choose the plus state?
No, it's an arbitrary. You can choose your initial state arbitrarily. Yeah, yeah. And of course, you know that if there are no photon losses, so this is just a boring unitary evolution of harmonic oscillators, so we can know precisely what is the state. And again, because we measure just the parity, we don't collapse the state, so we can save the information. Okay. So here, this is my proposed system. So let's go back here. So the problem here, or it's not the problem, some limitation here. Okay, this is as we said, this is a very nice platform. You can see here really they have these two resonators and the transmon, and you can see here we have the papers by Nissim Ofek from Quantum Machine or Serge Rosenblum from Weizmann Institute. So they showed really how to do error correction and track these jumps and correct for them. And this was the first, or what they claim to be the first demonstration of useful quantum error correction that you really improved the qubit performance. But now you see this is like a centimeter scale machined three-dimensional qubit. So if we want to have, okay, 1 qubit, it's nice, 2 qubits maybe, but if you want to have 1 million of those, right, so you need a very large room, and so the scalability of this platform is questionable. So we got inspired by this work, and what we propose is to replace this three-dimensional system with something which is planar on chip that you can hopefully scale for as many qubits as you want. And here you can see, okay, this is a representation of the system. So we're saying, okay, we will take mechanical resonator, this nanobeam that I showed you the illustration of it in the beginning, and this will be our harmonic oscillator. So you can take just a nanomechanical beam that you etch inside the diamond chip, and we will have a microwave resonator, just a planar coplanar waveguide resonator on chip. Again, something that you can do with optical or e-beam lithography. And to couple them, okay, now we have different components. So you need a different coupler, this non-linear component. So we suggest to use flux qubit. And here you can see the Hamiltonian. So you have this microwave resonator, mechanical resonator. The flux qubit is just a two-level system. And there is some coupling constant between this nonlinear flux qubit and each of the resonators. And it's very similar to things that we saw here in the course. But now we want to see, okay, we have what we really care about. Okay, we have this microwave resonator. This is the readout and control resonator. So we want to see if we send some microwave pulses to this resonator, to this microwave resonator, how it affects the mechanical resonator via this flux qubit. So to do it, we need to take this Hamiltonian. You see here, we don't see an interaction, a direct interaction between the two of them. So we want to move to a frame where we can explicitly see the interaction between these two systems. And to do this, we use a Schrieffer-Wolff transformation. And basically, the Schrieffer-Wolff transformation is another concept that we just use. You can write your Hamiltonian as some diagonal Hamiltonian plus an off-diagonal perturbation. And you want to apply, okay, if you apply a unitary transformation, you can expand it. This is just general, this is just a general way to expand a unitary transformation of the Hamiltonian. But what we see here, that you have, okay, this is our Hamiltonian, so when we apply this transformation S, we're going back to the same Hamiltonian plus some terms which depend on this S and its commutation relation with the diagonal Hamiltonian and the off-diagonal Hamiltonian. And if you choose this transformation S carefully, such that that S and H, the commutation relation equal to minus the perturbation, and you plug it here. Sorry, this should be H naught. Okay, so this term here will cancel the perturbation exactly, and then you will just remain with this term, which is just half the commutation relation between S and V plus I orders that you can neglect. Okay, so to first order, you remove the off-diagonal terms. So in our case, if you find this S and you apply it to the Hamiltonian, what we get is this H naught is just these diagonal terms. And you see that you got, okay, you have some dispersive shifts. So it's similar actually to what we saw here. If the qubit is excited with this sigma Z, if the qubit is excited, the frequencies of the elements is changed. And we got here this effective coupling between the two resonators. And just to, I don't know how much time do I have.
Right, Itamar, exactly. So, I mean, I would say not more than five minutes.
Okay.
Less is fine, but not more than 5 minutes.
Okay. So I think the important thing here, like the bottom of this proposal, is this coupling term here. So you got some effective coupling, which depends on all the parameters here. And you see here that you have this, okay, A dagger B plus A B dagger. So you have photon swap between the two microwave and mechanical resonator. And what's nice about it, it depends on the state of the qubit. So if I put my qubit in a superposition of 0 and 1, and I drive a coherent signal through the microwave resonator, I can get my superposition of coherent states inside the mechanical resonator. Okay, so this is the bottom line. So I just want to show here that we can have this cat state, which is the superposition of the coherent states inside the mechanical resonator just by driving a signal through the microwave resonator and putting the superconducting flux qubit in a superposition of 0 and 1. So we'll have here, plus beta and minus beta. Okay, so I will not go over all the details here on how exactly what are the parameters of all the beams and everything that we need, because we don't have time, but I just want to show you just how we realize it. So this is a diamond chip, and you can go with FIB or with RAE and just etch with an angle, and then you have these freestanding triangular beams. This will be our mechanical resonator. And you can see here, okay, it can have frequencies of 1 gigahertz and relatively nice quality factors of 30 or 50,000, but it needs to be very small in dimensions. And again, the flux qubit is just a superconducting loop with four Josephson junction. It's really behave like this two-level system near a special point here. When you apply a specific flux through this loop. And again, okay, how you fabricate it is just with a double angle evaporation. You have your suspended mask. And here also you can control the frequency and the current that is going through this loop. So you can control basically the interaction between all the components. So what we suggest is just to couple this the movement of this beam, if the beam is vibrating thermally here, and you apply magnetic flux in a perpendicular way, okay, so basically the vibration of the beam changes the flux that this qubit feels, and this is the origin of the coupling. I think we don't have more time, so I will stop here. But mainly what I wanted to show is that, we can, if you couple these two elements, as I showed you, you can generate these cat states and hopefully do this bosonic encoding of information, and the cat codes for correcting them on a chip. Everything is on a chip. So this is just some micrometer size element. Yeah, so I think I'll stop here.
Okay, thanks, Itamar. Actually, so we are a little bit out of time. I really have a question. If I understand correctly, the key feature is to be able to observe the parity, to measure the parity of the qubit, right? In order to make error correction. So how would you measure the parity here without measuring the qubit?
Without measuring the qubit? No, so actually you do measure the qubit. You measure the flux qubit, and the flux qubit will tell you the parity. You don't measure the cavity directly.
Okay, I see. Very nice. Okay, I see. This is a good answer. Okay, so unless there are other very urgent questions, I think we should summarize conclude this lecture for today, and we'll meet next week. Frontally, so I will come to Barilan, so we can meet. There will be an hybrid class next week.
Okay.
Okay, thanks, Itamar, and bye-bye to everyone.